Log on, tune in, find out. Another good idea from Cambridge.
André Bardow.
Yes. Thank you very much for the introduction. Thank you very much for inviting me, and thank you very much for shifting me in the program, because I have a big experiment at home going on that is delivered early. Apparently, at least that's the prediction from the doctors. So I have to leave this conference early because my son is coming up. Okay, but I don't want to leave before talking about my view on experimental design and share some things with you, and maybe throw at the theoreticians here. So I'm one of the barbarians, as we have been introduced this morning. I'm an engineer trying to gamble and make some use of these methods. And I want to look at two types of problems. One is the things we've been mostly talking about, hearing about this well-posed problems, but I've been also facing some problems where we have to face ill-posed problems, and I felt that there's a lack of theory there, and maybe I can be corrected, and but maybe I steer some future work for you to work on in the coming months. Okay, now I want to start out by telling you that I didn't do the work I will be presenting to you. Luckily, I'm a professor now, so the other people are doing the work. So the first part is actually done by Piotr Domagalski, and the last part has been mostly done by Ernesto Kriesen and Sven Kossak, and these are other people I've been collaborating in Aachen and in Delft, and I'm thankful for people who give me money. Okay, so what you have guessed is there are different parts. In the first part I want to talk about an application, and that's actually my introductory topic where I came across experimental design, that I was working on diffusion problems. Then I want to tell you something about ill-posed problems and the approach I've been developing for that. And the last thing is motivated from my current work. If you've seen, I'm now working in thermodynamics, and there our goal is to predict how physical matter behaves. So the last part is on prediction of physical property models. Okay, I've said I'm one of the barbarians, and I think Sandro Macchietto gave a nice introduction about the status of optimal experimental design, how it is used and applied in engineering at the moment. And so the problem is there are a couple of people are converted, but a lot of people, he said, don't like statistics, are scared of, and if they start to read a book, they are scared. And so for me, that was a problem also for me. And the other problem was, how do I communicate to my peers when I'm a young PhD student what I'm actually doing? Yeah, so I Fisher information metric, blah, 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 that's scary. So I came up with another thing, a marketing trick I wanted to share with you. So what I told my friends is, actually what I'm doing, I'm pimping experiments. Yeah, so that sounded cool, and then you caught the attention, and then you could maybe drag some of them along to the Fisher information and so forth. So why did I call my PhD thesis basically pimping experiments? I don't know how familiar you are with MTV TV programs, so I just want to go back and tell you what is actually where the title is taken from. Now there's a show called Pimp My Ride, where the basic concept is you take an old shabby car and then you pimp it. And pimping a car means you make it nicer, faster, and yeah, just better. So, and that's actually what my PhD research was. It was to pimp diffusion experiments. So what you see here is the best diffusion experiment in the world. It's not a tank, it's not a battleship, it's 9 meters long, it's several tons heavy, and it's really a good experiment, but my task was to pimp it, that is to make it nicer, faster, better, and so forth. Yeah? And what you kind of maybe see here, so what we did in my PhD, we used some fancy techniques, spectroscopy and so forth, all what is available to make it better, and combine this with a model-based approach. Yeah? So we used the techniques of optimal experimental design to make the best use of these advanced experimental facilities. Okay, so one task was a nice experiment, the other one was experimental design. And why did we pick diffusion experiments? That's written here. So I'm talking about diffusion in liquids, and there are a number of techniques already available how you could measure diffusion coefficients. But if you think about diffusion, probably you think it's slow. Diffusion is slow, that's true, and diffusion experiments are also very, very slow. And so you see here the important point, that is the time, and some of the standard techniques take days for a simple data point in a binary system that's only 2 components. I'm a chemical engineer. Such systems do not exist in practice, but even then they take days. And the battleship is actually the one below here, so the battleship takes 1 to 2 days. There are some faster techniques, but they are actually a lie. NMR measures something else. That's just from this review. And there's one good idea, but people don't like it very much. Okay, so what we did with the spectroscopy thing, we optimized the experiment, came up with a nicer one. But I don't want to talk about this today because I carried it on further to new techniques. And that's I want to share with you because we really wanted to compete with the very fast things and very easy. So I wanted to get away from spectroscopy but do something simple. And that's what I'm really talking today. Now, the technique and the insight how to get better diffusion experiments is experimental design, and I just want to introduce my view, how I get the message across to the engineers, and a similar picture has been shown yesterday by Professor van Impe. Now, I said engineers are scared by statements like this. So if you say, what is optimal experimental design? Yeah, you look at the 3 design variables and you try to maximize information. That's too vague for an engineer. It's not a screwdriver, it's not a car, that's too vague. So the picture I usually try to explain to an engineer why this is important is the drawing like here. Here have your parameter estimation objective. I have 2 different designs denoted by X, and this is my parameter. And they both, because I constructed the example, end up in the same minimum. So the engineer says, why should I care about experimental design? No, then I say, okay, down here you have some foggy area, that's your experimental error, you don't know really where you're heading, so down here you cannot trust your design. So if you map this foggy area into regions of uncertainty, you know that the uncertainty in the blue curve is much nicer than, much smaller than in the red curve, so we would prefer the blue curve over the red curve. And that's actually, now I can pull them into the mathematics and say, so actually what you want to do is maximize the curvature of your parameter estimation objective. And this is kind of what we've been seeing again and again these days. Okay, so what I want to do now is the parameter here down below is a diffusion coefficient. I want to set up an experiment that gets me the diffusion coefficient as easily as possible with very small and very quickly. And what I learned from my PhD research is you should make that experiment small, which makes sense because diffusion is slow. So if you make a small diffusion experiment, it will be fast. And actually, I misused an experimental setup a colleague of mine had owned. That is a so-called H-cell microchannel. And it's nice, and I like it because it's so simple, and it's just diffusion going on. So what do we have? It's called H-cell. We have 2 entries. And what you feed in is 2 solutions of different concentration. This is a small channel, so we only have laminar flow, very easy hydrodynamics. And here we colored them pink and a clear solution. They will meet here, they will flow in laminar flow side to side, but then they say, hey, here's a concentration gradient, why don't we diffuse? So they diffuse, 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 and then you split it again. And the people with the very good eyes see that here it's somewhat lighter and here somewhat pinkish. So diffusion has been taking place. And the question is, now that's a beautiful setup. It's very simple, it's very small, it's really, really small. So this is 1 millimeter. It's a small setup. What is nice, you can use small amounts. How do you run this in an optimal fashion? Because people have been using this setup, but how can you optimize it? And so we went about model-based experimental design. And okay, first I should tell you how does it really look like. So this is a small setup. You have a syringe pump that puts the fluid in, and here you see it better. The idea conceptually, so I have different solutions, they mix, and then I have mixed solutions depending on the size. Just for the engineers, the important thing is the Reynolds number is really low, so it's really laminar flow, and the Peclet number is another thing that says that in this direction I have only convection, so it's dominated by convection, and so I have streamwise. In this direction I have only convection, and this size diffusion. So it's kind of a simple setup. And actually, the main trick of the work we have been doing has been in the modeling. And here's the model we've been actually using in a very simplified form, because 2 people have been working on this problem. So one have been the engineering theoreticians. They did 3D simulations of this channel, because you can create some interesting phenomena in this kind of flow by the boundary conditions. And the other people have been the people using this as an experiment. And they used the simplest model possible. What we tried is to combine these things and to use a model complicated enough to get the interesting physics, but simple enough to do the way I'm able to do experimental design. And so what you end up is with a diffusion equation. This is the x coordinate along the coordinate, and then I have in the diameter I have diffusion. And what is important is that you take the stream profile into account. And here we simply integrated an analytical solution. But actually that was the key, because the other people just assumed either it's plug flow or that it's a whole 3D thing. So if you have such a simple model, and I'm happy to discuss details, you can compute the concentration profile. And so what you see here is that's a jump at the beginning, low concentration here, high there. Then along the coordinate, the thing is equilibrating, as you would expect from a diffusion experiment. We ask ourselves two things. One is, if I would be able to measure locally, where should we measure? And the other one is, how long should we measure, or what should be the flow rate? And obviously there must be an optimal flow rate, because if the channel is very, very short, I would have no diffusion. If it's very, very long, it would be perfectly mixed. So there must be an optimal time in between. Yeah. And so we computed the Fisher information, and here it's also a scalar, because I'm just in a binary system going for binary systems, and this is the result. Now, so first thing what you see is there is indeed a finite optimal length of the channel. So this is the length or a residence time. There is an optimum one where we get the most information on the diffusion coefficient, as I just explained. And the second result, which is maybe more hidden, but maybe more surprising, if you would have to measure at only one point, we would not measure at the jump of the concentration. Maybe most of you would have betted to measure at the jump. Actually, it's more beneficial to measure down at the wall. And that is because the boundary condition is a no flux boundary condition. It's a kind of reflecting. And so you get an amplification of the signal at the wall. So that's just a nice result. But we cannot measure locally. We mix the streams in the end anyhow, because here I didn't want to use a laser. So the important result was for us, there is an optimal Fourier number, and so we went into the lab and tested this. And this is a result I'm really happy with, because actually I said, okay, this has to be the result, and what you see here is the dotted line is what you've just seen. That is the Fisher information, and we just scaled it and say there's an optimal Fourier number. And then Piotr went into the lab, did the experiments, did them a couple of times, and then looked what is the variance of the diffusion coefficients, what I get, and this is what is plotted here. So you very nicely really follow the shape. Yeah, this is information, this is variance, and you really find this minimum in the experiments. Yeah? So there's clearly an optimal number, and even quantitatively it matches quite well. What is important from the engineering point to mention, all other people who have been working with the setup up to now used Fourier numbers up to 100s. So really the case where there's basically no information on diffusion. But the good thing is that the model is even simpler than the one we have been using, and that's what they liked. But they have been really missing out the information. So we now have the setup, and we can gamble with it, and that's what engineers are happy. So it's quite easy to study temperature dependence. It's quite easy to study concentration dependence in the simple setup. And so we have now a device to perform robustly and flexible diffusion experiment. And what is also important for practical applications, that we don't use much of stuff that we put in. So if you have some new product, something newly developed, and you want to learn about diffusion, it's always bad when you say, okay, give me a liter of that, and then I tell you the diffusion coefficient. So we have very small syringes, and you give me a couple of milliliters, and I can give you very accurate data. So this is just another success story of optimal experimental design, and we should be all proud and happy that we work in the field. Okay, so our hope is in the next edition of the book that there's going to be our setup added to this, and it's really just a question of minutes that you now can perform, get high accuracy diffusion coefficients. Okay, but the question then was, actually, can we not do better? And what I've just shown you is that these diffusion coefficients are actually a function of concentration. And what we've been doing on the last slide, and that's what you traditionally do, you do one experiment, so this is diffusion coefficient over concentration. And so the trick is to get the concentration dependence. You do a lot of experiments. And just to tell you, these are experiments that take 2 days each one. So there's a pure PhD student doing all of these experiments. And what we've been asking ourselves is, can we not do it more easily? For example, and what we said is, if we put in the pure fluids on this side and that side, all the concentration should have occurred in the meantime, and can I not estimate the whole function from a simple experiment? To be quite honest, you will not get it from these lumped outlets I've been showing you, but what we did before, and this is data shown here, that's what is it, dotted line, With the Raman experiments, where we got local information on the concentration profile, you can really get the concentration dependence from one experiment, and that is what is indicated here. So that's possible, but you pay a price, because I'm not now going for a constant number or 2 parameters, I'm now going for a function. Yeah? And that's what I meant in the introduction. I said, okay, you can get a whole function from this data. We are now able to generate so much data, but you really have to solve an ill-posed problems and to take care that you get a function. So I want to briefly summarize how we analyze ill-posed problems where our solution does not continuously depend on the data. So in an ill-posed problems, I can have simulation, my noise goes down, but the solution still strays. So that's a bad point. And the most common way to solve these kinds of problems, most popular one is actually Tikhonov regularization, where instead of you have your normal estimation problem, or what I just said, this one would explode, the error would explode. So what we do add is a penalty term on our unknown function, which are here called R. And this is a regularization term where you, for example, penalize the size of your solution or the second derivative, that it's not too much fluctuating. Yeah? So here, that's the way people in ill-posed problems like to write this as integral equation, because then you see that the forward operator is smoothing and you're trying to invert a smoothing operator. That's a bad thing. So what you do is, what I show here, you have your standard kind of lack of fit term, that's for me least squares as an engineer, and then I penalize this for smoothness. So that works actually, but you pay a price. So the lack of fit term measures the variance, and then I add a penalty term which also adds bias to my solution. But only this way I get a stable solution. And actually, if you solve this ill-posed problems, this bias variance trade-offs, that's the thing you have to work on. And that's shown here in the right plot. So I have this regularization parameter lambda, that is the factor in front of my penalty term. If I don't have it, my solution simply explodes from the error. And then I add, for example, if I penalize the second derivative, I say you have to be a straight line. So I say, okay, you cannot explode, you should be a straight line. If I make this very large, no matter what the data was, I get a straight line, and I have to somehow balance this. That's standard theory, and you can find thick textbooks on this topic, how to solve the ill-posed problems. And I use these kinds of techniques to get my diffusion coefficient. But I was always wondering, what consequences does this have for experimental design? And actually, I found very little on people working on experimental design for ill-posed problems, and what I found is where people applied the classical theory. So the classical theory, as I introduced to you, is to me this picture. So what we classically do, we maximize the curvature of this curve. So, so that's what we are going for. But if you see this now in the light of the previous slide, that might be actually not the wisest thing to do. Because in the previous slide, I said for an ill-posed problem, I only get a stable solution when I have to add bias to the solution. So actually, I bias my solution so that true value might actually be sitting here. If I apply the standard design theory, we're actually focusing only on the variance. The bias is missing. So in a sense, I said this. So what we are doing, if we apply standard theory, you might estimate the wrong solution, but with least uncertainty. Yeah. So that made me somewhat nervous. So so what I tried to do is to come up with a modified criterion, which I called, I also had an abbreviation, but I think it's at least pronounceable. I called it meter, because I want to minimize the expected total error. And it should rectify what would be done with a classical design criterion. Usually, okay, optimal experimental design in general looks at the best determination of our unknown parameter or function. In the classical approach, and I attributed to Box and Lucas, you would only look at the parameter variance. But what you should do for ill-posed problems, and that I say for Box and Draper, because they look at similar things for surface response models, you really should look at the expected total error in your estimate. And that's what I've written down here. And if you do the math for the Tikhonov regularization, you see that actually this objective function will have two terms, and you can identify both terms, because one really measures the bias. So here you have the lambda, the regularization parameter. If this is 0, then this is the inverse, so this term would drop out. So I have one in my objective function, one thing that measures the bias due to regularization, and the second term actually has a trace, the measurement error. So this is the variance in the estimate. And actually, if you analyze, so this objective function for an optimal experimental design has the two contributions. Says how far am I off from the solution, and how big is the variance I have to expect. And if I want to minimize this, I really capture this variance bias trade-off in the experimental design. What is maybe quite interesting to see is if you drop this term, this one actually reduces to the A criterion. So it's actually for an unregularized solution, so that also gives you some good feeling at least that it comes from something that is useful. Okay, so I derived this, and then I looked, and I want to only discuss one of the most simplest examples, but that has the advantage that I do understand it, and I'm happy to see that's the approach the mathematicians are also taking. So the most simple example to me was numerical differentiation. And I put this in a chemical engineering context, but I can drop this here. So basically the idea, I have some data that is corrupted by noise, and I want to have the time derivative. To me, it's concentration data, I want to know the reaction rate. So this is known to be an ill-posed problem, because if you add a very small sinus, if the frequency go up, you can even with a small magnitude make the solution explode. And numerical differentiation, a naive engineer would do this by finite differences. So what I proposed is to estimate this unknown function r, the derivative by finite differences, backward differences, and what everybody knows is, and I demonstrated here, so if my function is a sine, I expect a cosine. Now, if I take two core samples, these are the crosses here, that would be the finite differences solution, which vaguely resembles a cosine, maybe because I sampled two cores. Then I say, give me all the data you have. So I gave you all the data I had, and if you then perform finite differences, your solution simply explodes. That's what I meant before. And I want you to notice that I changed the scale here. That's because I have low frequency noise, the solution simply explodes. And so my design variable was to say, what is the right sampling frequency in order to get the optimal sampling frequency in this optimal design. So I applied the criterion I've been just introducing to you, and that's the result that you get. So this is the expected error I was computing over the sampling frequency, and the blue line is the optimization criterion. And the good news is there is an optimum, so there is an optimal sampling time that we can get, and I can also, and that's the nice part of it, I can also analyze what is the bias contribution and what is the variance contributions. And that's the red line is the bias, and as you would have expected, the bias goes up if I take longer sampling time that I've just shown in the example, and if I sample too fine with a too fine grid, then the variance contribution explodes. So that's a prediction. Here's a prediction for different levels of the measurement noise, so you get different, so the optimal design changes, and this is a numerical computation of the same thing, and you're seeing they correspond very, very well. Now, okay, so I proposed again something new. I apologize, so I should justify that it is better what you would usually get if you apply a standard criterion to the same situation. So here you see the same plot I showed before, and on the right axis I showed the E optimal criterion, but it's the same for all criteria, and that's the black line you see here, and I want to maximize it in this situation. So you see a standard criterion, and any standard criterion would go for the largest step size. And actually that's completely reasonable, because this criterion I'm asking, give me the solution with the minimal variance. And if I do finite differences and I take the points as far as apart as from each other, then my noise does not influence the solution. So it's completely wrong, but it doesn't change. So that's very reliable, and that's what we ask this criterion for. So, and this is what this criterion does. And so the standard criteria for these kinds of problems are even qualitatively in error. Okay, so so the criterion we propose, which is in this Box-Draper school, really captures this trade-off, and the classical methods are even qualitatively wrong. I showed this for a linear problem. You can apply the standard linearization techniques as usual. There is obviously a catch, and that's that even for the linear case, you need now to know your unknown function, because I have to put it in to compute the bias. Yeah. Okay, what I didn't discuss, the regularization parameter, which is a tricky thing. You can even use this in the design as an optimization parameter, and you have to know the unknown function a priori. But yeah, robust designs have been proposed, and actually if you read the paper, they also naturally extend to this kind of problems. So if you know something about your function class, even if you know very little, you will be safer using these kinds of designs in ill-posed problems than without. Okay. Good. And actually, the original schedule of this conference was perfectly designed, because if the mathematicians are not convinced, Stefanie Biedermann is going to present tomorrow after my original slot the mathematical side of the story, and it coincides as far as I understand her work, so I'm quite happy with that. Okay, so we have these designs, and but I want to stretch the method and show you some of the problems we are facing now in thermodynamics, the field I'm currently working on. Because for us, what we want to do as thermodynamicists is, our goal is to, if you have molecules, to predict how the world is behaving. Yeah, just from the structure of molecules. That's a big thing in thermodynamics. And actually, it's kind of, we are fighting to make experiments useless. Yeah? That we have predictive theories. So what I've just been talking about, to design better experiments, is actually my final hope when I retire someday, is that experiments are obsolete. Yeah? So what we are actually aiming for is, you give me a molecular structure, you say I'm using this molecule in a process and I want to completely predict this. And what is very important is to have predictive property models. Just as an example, you say I'm using a process where I have different molecules, I give you molecular structure, and if I talk again about diffusion, then I have a model that only based on information of the molecular structure could predict the diffusion. That's even faster than our microcell, if I just can predict it like this. So that's what we are aiming for. And actually, the experiments we are conducting are very often used to test predictive theories. Yeah? So we are developing theories, and then still nowadays we have to test these theories. And in this context, a problem arises. Now I'm developing this beautiful diffusion theory, which should be applicable to all molecules in the world. I'm young and ambitious. The question is then, which molecule do I use to test my theory? So that's then, which are the good ones? So in principle, you could say, okay, so simply write all molecules in the world as degree of freedom of your experimental design, and it will tell you. Now I showed a little bit of dots. Yeah. So if you look up the web, I think there are about 50 million known molecules at the moment listed. So I would have a design problem which is ugly already, with 50 million discrete variables, design variables. So that's not possible. But at least we can approach this problem, and it's really, really something that is practical. And I want to show you how we approach this problem using actually the predictive models we have here. Okay, so what I'm now talking about, and I want to emphasize, is the very important stage we usually have first, where we try to get the right model structure. So usually we have two stages in experimental design, where we look at the model structures, where we do experimental design for model discrimination, we do our vicious cycle, then I have a model structure, and then I go for the parameters. And actually, we very much discuss this side, and as engineer, we have physically based models, so it's always also very, very important to get the right model structure, because they are not simple regression models. And what I want to discuss is, how do I integrate the choice of the test species in such an experimental design? And I just want to motivate the problem I've been working upon, and it's a diffusion problem. If you don't care about diffusion, I will summarize the message in the end. Basically, the dilemma of diffusion is, what you measure are so-called fixed diffusion coefficients, but these are empirical. And there's a beautiful theory by Max Verstappen, based on linear irreversible thermodynamics, and there people do all the predictive models and so forth. But to get from here to there, you have to multiply it by the so-called thermodynamic factor, and that nobody knows. So that's a really bad thing. So you have a beautiful theory, but every theory matches the results, because you can always blame it on this factor. And this is now for the diffusion experts. What we came up with a nice way, that in a situation where you have a multi-component diffusion, as shown here, so it's not just a constant, it's a matrix. If you go to infinite dilution, this factor drops out, and you get expressions like this. I don't want you to study it in detail, but the important thing is, here is no big gamma. So this thermo factor drops out, and I can study diffusion. And in particular, these diffusion coefficients I can estimate with the NMR, which was the other quick thing, but they measure other diffusion. This is self-diffusion or I can do this very efficiently by molecular simulations. Okay, for the people who didn't care about diffusion, the important bit is I have 5 different models that describe this situation, and all of them claim to be predictive models, but and the question is, how do we discriminate them? Yeah, so I have the classical question, optimal experimental design for model discrimination, and what these designs classically answer is the question, for example, these are the 5 predictions, yeah? These are the 5 different models predicted, and what we typically ask, at which concentration should I measure? Yeah, and there's very stupid concentrations because these values have to be the same at the corners, and there's much better values in the middle, and I just write, here's a simple Hunter-Reiner, and we use this method from Buzzi and Ferraris, which takes the parameter uncertainty into account. Yeah, so that's the classical case. That's what these methods are worked for. So the question I've been posing is, which chemical system should I use to test my theories? And just to point out that this does have an impact, I'm showing here a ternary system, the cyclohexane, dioxane plus toluene, and in this system I just changed dioxane for N-hexane. And what you see is that the deviation between the models becomes much larger, and just imagine that your measurement device has an inaccuracy of this. This is your error bar. So in this case, I could not discriminate any of the models, but if I would test the N-hexane system, and actually I have no preference for either one, I could clearly, if the measurement point is here, I could clearly rule out the other ones. Yeah? So what is clear, there is a big handle to do this, to pick the species you are looking at. The problem is that you have to integrate these 50 million degrees of freedom. So that's ugly. So how can you do this? Now actually we look for the maximum, that a molecule that has a maximum deviation. So what we employ is a technique that has been developed in chemical engineering, what we call chemical product design. Because actually what we are doing now is we are trying to find a molecule that has a specific property. And that's what chemical engineers do. So we look for something that is a better hairspray, or a better soap, or a better, I don't know, something for your car. So, and the work process is that's more heuristic and so forth. What you'd have to do is first define your needs in a proper way. You generate ideas, you screen them, and then you produce it. But this framework can be translated to our design problem. Define the needs. I just said this might be my objective function from model discrimination. And then we can use tools that are already available from computer-aided molecular design. So what we do we have so-called group contribution methods, where we have molecular blocks. So these are parts of molecules, I hope you can see. And with group contribution methods, we can estimate what the properties are. So we can then generate ideas to bake them, and then we look at the best ones, and then we perform the experiments. Let me show this in a little bit of detail. So this is the standard workflow where I have a mathematical model, I use it for design, I run the experiment, and then I analyze it using the mathematical model. Now the important bit is now that my model has now 2 parts. One is a physical property model, and the rest describes the rest of the experiment, where I use my physical property. And my physical property model is usually fed with some information about the molecular structure. So I have to tell you which mixture I'm using. Was it these 3 components? And usually I have to feed in some mixture properties. And what we're now introducing is here an extra loop that is indicated here, that in the experimental design we have the usual design parameters. That's the concentration I was just pointing out. But I also have information about my mixture. And we solve now in an optimal experimental design problem, we generate a target value for our mixture's properties. And this I can then use in these group contribution methods to get the optimal solution. So let me discuss this for this specific example. So how does our mathematical model look like? That's the model that's the 5 physical property models. So it's just 5 models, that's the important information. I can predict a mixture property, but I do need some input data. And this is shown here. Basically, I do need binary data. You have seen that all the values were the same in the corner. And these are kind of the corner points I need to put in. Basically, this describes, that's the only information my experiment has, which mixture I'm using. That's a binary point. And then I use these 5 different models in this big model. This describes actually the process. So I now have 2 types of variables. These variables describe the mixture I'm using at, and here I have other variables like the concentration, which is a regular design variable. So now I have 2 classes of variables. This is concentration, standard, and this is mixture specific. So this is the diffusion of a specific component of a specific component of a specific component. And what we now do is in our optimal experimental design. This is my model. I perform, and I here wrote it again in the simple form. We simply relax the optimization problem. So we have freedom in these parameters. We forget that we have 50 million discrete molecules, but I compute any diffusion coefficient which might be useful in order to generate a target for our algorithm, later on for our search algorithm. So what we solve is a relaxed problem where we forget about the discreteness, and this way we get a target of the property. And with this target we can feed this group contribution methods. Let me show you this example, and there's one more technical note. Actually, we don't need to optimize diffusion coefficients, but the important parameter is the square root of the molar weight of the viscosity and the molar volume. And what you can use is in our design problem say, what is the optimal combination of these two variables to perform the best model discrimination? And this is the objective function that you get. It has some minimum range, but we want to maximize this. And what you see is you want a small molecule that has a large viscosity. No, a small viscosity. This ratio should be large. This ratio should be large. So the viscosity should be large. So that's kind of small. That's kind of difficult. But this is the target. So what we did is, by relaxing the molecular parameters, we can now generate a target for these group contribution methods. Tell me, go into this corner, and these algorithms, and there's even software available, can generate a list of molecules that is small and has this ratio square root over viscosity also large. Okay, and this is what you then get. You get different molecules, and I don't want to discuss the molecules in detail. But what is interesting, and that's why I think it's very useful. This is the objective function, and it's related to the number of experiments you need to do. So this one is a factor of 6 higher. This means if you run this system, if you would use this system, you would need 6 times as many experiments compared to this one. And this is just to show you the potential, because these are the top 3 molecules I've been finding. If I would have used the classical approach, which is which bottle do I still have in the cupboard, I would probably not hit one of the top 3 molecules. So, so there's a big potential if you integrate this choice of the right molecules, so the mixture design, but not in a composition way, but really in the physical component structure. And this is just to show you the potential here. I said this is what we started with, and this is the objective function, so we really stretch this apart. And actually we applied this because I'm method driven. I try to forget the result, and the result is of the 5 models, none is good. But that's no surprise because nobody has been able to test them. But in the meantime, we came up with a better idea, and there's a reference down here. Okay, so you can even extend the framework for experimental design to mixtures. I think it's very convenient. You can do it for model discrimination, the same technique, this relaxation technique, and integrating this group contribution method works for all problems. And I think it's really interesting because it saves experimental effort. And the other thing is also we can analyze which molecules might be the critical one. Yeah, so we would say I have a good model, but it does not solve the whole world. But all very polar components will be terrible. But I know this. I can just test this systematically. Okay, so this is my short summary. I think for us, it's a great tool to use optimal experimental design because it really leads to non-intuitive designs. Yeah, so we're used to this, what's left in the cupboard, what has been done before, so it really helps us. I think what is important for engineers, and this has been mentioned by Sandro yesterday, that there's software appearing, and that is a big issue, that they can do it efficiently. I'm very happy to see that on the ill-post problem, there's the theory now being developed and other formulations also. And the last thing is that even such a complex problem as mixture selection could be integrated. So for us, it's mandatory to do this, to apply this, and I'm happy to learn about new contributions. But actually, I think there's quite some things available, and to me, the most important thing is to do it at all. That's what I teach. That's why I use the simple pictures, and I teach my students, for example, just do it, even with the worst. And if we're fighting about A and E and D, and it's very religious here, just do anything, it will be better than not doing it. That's my personal comment, and you can kill me if you feel like it, because now my talk is over. Thank you.
I wonder how this in the case where you estimate derivatives from this function, you're choosing a discretization for the derivative approximation in essence, right? That's what you.
You're in the ill-posed part, huh?
Yes,
Yeah, okay.
exactly. So how? So there is this reminds me of a technique of regularization. It's called regularization by projection, where you choose a approximation space in such a way that you can minimize the error.
Yeah.
This trade-off between regularization error and so how does this compare to this strategy?
Actually, I think you could do the same analysis for this regularization technique. I think it's, in a sense, it's what I did. That's also why the numerical example was not perfect. Because I misstretch. Actually, I project on piecewise constant functions and say they should be long enough not to get all the noise. So that's what I did. But essentially, if you can, the important point is you should not look at the variance, but the expected total error. And you can do the same computation for the projections, I believe. It changes somewhat the philosophy because I have to know my unknown function even for the linear case and so forth, but I think it's important. But it should be applicable.
So in the box-Draper approach you mentioned, the term you don't account for is a polynomial of bigger degree. But this approach has been extended quite a lot and has been discussed in design literature and estimation literature for in many papers. And of course, all this mean squared error split into variance plus bias, and it's been discussed a huge amount of time in design experimental literature where non-parametric classes and stuff like that. So you haven't mentioned that at all, and it looks suspiciously the same. I mean, so your criterion looks suspiciously one of particular cases, especially if you want to know the answer, but you don't want to answer. You can do Bayesian with respect to your possible answer, minimax case, or God knows what. All this Kolmogorov-Witz problems and lots of literature. I don't know. You haven't mentioned any of that when you introduced your criterion, which is simply mean squared error.
Okay, I'm sorry if I harmed your feelings.
No, you didn't.
But okay, what I did, I think I mentioned to me, at least, and I'm not as knowledgeable, so I'm very happy about the opportunity to learn from you about this. So let's say, and I mentioned box-Draper because I was aware of this. I can only tell you that even with the mathematicians working in the inverse problem in a general case, if you study that literature, what has been done is to use the standard design criteria. That I can say.
Yeah, but box-Draper is 62 or something.
I know. So I can only, I'm happy to learn where this has been exactly written down, and I propose this.
No, I don't know if that was exactly written down, but there's huge literature which extended box-Draper to God knows where. There's so much literature in design of experiments and statistics on these topics.
I mean, if you want to get right hyper-modern, you could say, well, perhaps the most famous regularization used in statistics is lasso. Okay, so the question then you ask you a question: are there any papers on experimental design using lasso type regularization? And the answer is yes. There's about 3, and there have been in the last year. And you could just go on Google and put lasso and experimental design. You take any of the regularization methods that Anatole has been talking about. There's probably some beginning to be there's either some old design stuff on it or some more recent design stuff on it. So it's an interesting literature, the interface between regularization and experimental design. It's not complete, but it's pretty extensive.
Can I just make a comment? You told us with absolute horror that some of your experiments take 2 days to get a result. Think about those of us in agriculture. It takes 1 whole growing season to get a result. So just a contrasted approach.
Yeah, that's okay. Maybe that's the reason why the field started in agriculture. Yeah. And I'm.
The other question?
Maybe I didn't catch it. Well, I mean, your comment on molecular dynamics not being sufficiently accurate. Because I would think that these problems have been, the diffusion coefficients, the ones you showed, have been solved for, I don't know, I would imagine. Is it not the case? Or is it not accurate enough? In particular for those molecules.
Yeah, it's no. Actually, the predictive theories are really bad, and in particular for multi-component mixtures. So I've been showing this for binary. Yeah, just to give you the reference, the guy who invented this battleship I've been showing, he's been suggesting if you study a 5-component mixture, which is not a lot of components, that's nice work for a PhD thesis. Yeah, so that's more than to get one data point. So that's, I think in his work it's 4 agricultural seasons. Yeah, if you take this as a measurement.
Or even high-profile MD calculations and supercomputers and all that.
No, you can compute it, and that's what I just said. We used MD also to compute it. Yeah, so you can do it, but then the question, you simply translate your problem to say, do you have the right force field? Yeah, and the force fields actually, so how to describe a molecule.
But you can compute it for those simple molecules. It's
Yeah, but I want to be general for any molecule, and then it's bad. And actually, the force fields are usually parameterized for equilibrium thermodynamics data, vapor pressure, densities, and so forth. And transport is usually the worst part of it. One reason, because the simulations also take forever.
okay. Well, all right. Well, there are tricks. I don't know.
Okay, I think we'll just move on to the next talk. Thanks for coming in.